to the cloud. So in example 2 on page 72, you have the given region A has an area of 1.5, right? And the integral over the interval of 0 to 6 of that function, f of x dx is equal to 3.5. We evaluate the following integrals. And it really comes down to the understanding of what an integral tells us, right? What an integral gives us is the accumulated area over an interval, right? But that area is a net area that could be either positive or negative, right? So I'm going to do an extreme close-up here and just show you real quick. I talked about this last time, but it wasn't really, critical. But at this point, it kind of is. So on this interval here, you would have a rectangle. If we were to use rectangular approximation, we would have an arbitrary rectangle over this interval that would have a width of dx. Right? Its height would be based off of the function, but its height would be some negative value. Right? So, I mean, we could go dx, or I'll even go delta x just to give it some actual real width. But the height is some negative value of y. Right? So the area over that interval, right, this area here would be negative y delta x. All right. Now, if that rectangle were of infinitesimal width, then I would say it's negative y dx, but it really doesn't matter at this point. It's really all about the sign, right? So this is a negative area. All right. Whereas over this interval, let's say I put it here, an arbitrary rectangle. That has some thickness delta x. The height of that rectangle would be some y value. The area of this rectangle would be y delta x, right? That's going to be some positive area. Right, that's going to be some positive area, right? So what that means is, if we were to accumulate all the different areas that one could have over this interval, so starting with the 2 and going to the 6, for example, so all the different possible rectangles that you could have over that interval. Try to make it look a little nicer. Every one of these little rectangles that could exist. I'm just drawing them as straight lines for brevity, but you just kind of imagine that these are just really thin rectangles. If I were to take all of these rectangles and add up their accumulation of areas, I would get some positive area over this interval. Right? And so if I could get infinitely many of those rectangles in there, go with, that might be too dark, but we'll see. No, that's going to work. Just a little on the thick side. All right, if I get the accumulation of all possible rectangles over this interval, then I would have a positive area. All right. All right, so that's a lot to really just get at the idea that if the region is above the x-axis, it's going to yield a positive area. If the region is below the x-axis, so if I do the same thing just with this little region here, so get all the different possible rectangles that I could possibly have over that interval, and each one would have a negative y value associated with it. So then the area over this interval would have to be negative. I missed a spot. All right. So that's a lot of explanation to get at the idea that when it says region A has an area of 1.5, that must be a total area, right? That must be if somebody were to actually measure it. Yeah, like prior to this course, I'd say find the area of that region and actually take the x-axis, y-axis out of it. You know, just give somebody that figure and say find the area, you know, using whatever technique they want. They would have come up with a 1.5 because they didn't have any context associated with it, right? But because it's below the x-axis, what we get from this is that this as a total area over that interval would correspond to a net area of negative 1.5. The negative being because it's below the x-axis. But it's only negative because it's below the x-axis because the corresponding value of y is negative, right? So it's an extra layer of explanation there that you don't always need, but it's nice to know why these things work the way they do. But what that gives us is a definite integral over the interval of 0 to 2 of the function f of x dx being equal to negative 1.5. It gives us a relationship. Okay. Now, one of the properties that we learned tells us that if we break up an interval and find the area, the net area over each part, and then add it together, that'll give us the complete net area over the interval. So if I take the integral, I don't know why that happened the way it did. If I take the integral over the interval of 0 to 2 of f of x dx and add to it the integral over the interval of 2 to 6, you know, going the rest of the way of f of x dx, that would give me really just going from beginning to end it all in one shot. So this would be equivalent to the integral over the interval of 0 to 6 of f of x dx. All right. So since we now know that this is negative 1.5, and they told us over here that the integral over the interval of 0 to 6 of f of x dx is 3.5, we now have the means to solve for the other part, right? The area, the net area over the other interval, you know, that red area, right? Which was unknown prior to this. But now all I have to do is add a 1.5 to both sides, and I would get, or I would be able to draw the conclusion that the integral over the interval of 0 to 2 of f of x dx is equal to 5. All right, just by piecing things together. Now, I haven't even started answering the questions, but I can tell you that we already got a good chunk of them done just based off of the analysis of the graph. All right. A was just asking, what is the integral associated with the interval over 0 to 2? That was one of the first things we figured out. That's negative 1.5. All right. Part B, that's a little weird, but also doable. All right. It says the integral over the interval of 0 to 6 of 2 plus f of x dx. But I can apply the addition rule for integrals, which works the same way as the addition rule for everything else, whether it's limits, derivatives, or antiderivatives. You can split by the sum. So I'd have 0 to 6 of 2 dx the integral over the interval of 0 to 6 of the integrand 2 with respect to x plus the integral over the interval of 0 to 6 of f of x dx. Now, this piece is actually an ordinary function, as in something that we could determine its value without having to go to the diagram. Right? We can do it on Desmos if we want. I'll show you a different way in a sec, but the other part is just 3.5 because that was given. That's kind of nice, right? But this piece, I mean, and I got to say, as you go forward, it's going to be more and more difficult to keep in mind what an integral is really telling you, because you're going to learn all these different skills for integration. And to keep it straight, keep all those skills straight in your mind while also understanding what it is you're ultimately finding. It's not the easiest thing in the world. But if you always have in your mind that you're looking for the area bounded between this function of x, now it doesn't have an x in it, so it's a constant function, and the corresponding axis. Now, in this case, the axis is x, right? So I'm looking for the area. So it gives the area between f of x equals 2 and the x-axis over the interval of 0 to 6. So from x equals 0 to x equals 6. I mean, that's what that notation is telling us. In fact, an alternate form of this notation would be to say, just had a moment of panic there. Also, the lights blink, so I'm starting to get really worried. I thought for a second I wasn't recording, that would have been bad. But alternate form of this notation, which I'm just going to write this one time, and then I'm going to erase it almost immediately, would be to say the integral over the interval of x equals 0 to x equals 6. Right? A lot of folks will write their integrals that way, because your bounds of integration have to be consistent with the variable of integration, right? But it gets a little overkill. But when you think about the graphical representation, let me get rid of this nice Poisson distribution from statistics. It's weird to think, if you've ever took a stat class, it's weird to think that there will be a moment when the statistic, like the rules for all the things that you learned about, like normal curves and stuff like that, will become clearer based on your knowledge of antiderivatives. It's just like, how do the two things go together? They do, and it's glorious. But when I say it gives the area between f of x equals 2, so that's a horizontal line, it's a constant function, over the interval of x equals 0 to x equals 6. All right. Now, if I want to get really, really cute about it, I could try to do the shading, which would be, I'll just kind of do this as a side computation. It would be x, I'll do it as y is less than or equal to 2. I'll do the shading actually between 0 and 2. So that's only that strip, but only between 0 and 6. All right, so that integral is telling you to find this area. And it's like, oh, well, why didn't you just say that to begin with? It's 12. I mean, you could put the integral in your calculator and that'd be fine, but the visual representation kind of gets the point across a little nicer. Now, we also kind of want to think, all right, well, can we do this even without creating the graph? for a constant function, it's actually pretty cool. All you have to do is figure out what the distance is between your two x bounds, because you know your y bound or your y value isn't changing. That distance is always 2 units away from the x-axis in this case. So since there's 6 units separating my low bound and my upper bound, it's just a matter of taking that difference and multiplying it by my integrand, right? It's not a rule that people absolutely need to know because you have calculators to do it for you, but it's nice when you recognize it. You know, it's just the amount of time it takes to type it into a calculator. You know, it's way longer than it would take to actually figure it out in your head, right? So for a constant function, that I'll call f of x equals c. If we're integrating over the interval of a to b, that function c, the result is just going to be the difference between a and b times c. And it's not really a stretch to prove that, because it really is just a fundamental theorem of calculus just at work. Okay, because if I anti-differentiated, you know, so I'll just kind of call this the rule, and I'll just show you a more brute force way of verifying it. But if I were to say, all right, I'll take the antiderivative of c, some constant c, it would be cx over the interval of x equals a to x equals b. So c times b minus c times a. And then I pull out the c, and I get b times a, right? So this is really just a proof of that. Not anything I'm going to ask you to do, but nice to know. Okay, I can't get this line to go horizontal for me. So I'm just going to use a highlighter. All right, so that's a little constant rule, because now if I, like, for example, over the same interval, if I had a constant function of, like, let's say 10, I would know the antiderivative would be 60, because the difference between the bounds is 6 times the integrand, which would be 10. 10 times 6 would be 60, and then there you would have it. You know, so it's kind of nice. Right. Just keeping it on the same screen here, I'll jump down to D. And also D looks a little less complicated than this baby right there, the absolute value one. That's kind of a cool problem we'll get to in a sec. So constant multiple rule, factor out the -2 over the interval of 0 to 2, f of x dx. We already figured this out. That was a, -1. I'm sorry, -1.5 multiplied by -2 gives you a 3. And really, to think about it, we're doing all this without ever knowing what the function is, just a general idea of what the shape of it is. It looks like it might be some part of a kind of a composite function between maybe a trig and some sort of exponential or log function. But we don't really know. So, but we can get all these answers just by knowing a couple of pieces of information about it. Now, part C is a different story, right? Part C is actually pretty easy if you know what an absolute value function looks like, right? So here I'm gonna remediate for a second, because in my experience, it's a topic that's almost completely ignored in the pre-calculus courses. Whenever you're taking the absolute value of a number, we know that we're just negating it to make it positive if it's negative, and we're keeping it as is if it's already positive. AKA, we're dropping any negatives that might be there. All right. So the question would be, why would that be any different if it's a graphical representation? So, and I always thought this was crazy, because when I was first teaching absolute value function graphs in like algebra 2 high school level, I was teaching it in a way that made it way more complicated than it needed to be, just because I didn't know. And then I was looking at it, I was like, wait a minute, why is this even hard? Like, for example, let's say I have a function y equals x squared minus 1. All right. You see part of this function's positive and part of this function's negative, right? Any part of the graph that's below the x-axis, so if I say y is less than or equal to 0, let's make that red actually. That would be the part where the graph is negative, right? Anything that's above the x-axis is where the graph would be positive, right? So just like if I had the number -2, regardless of the context, if I wanted to find the absolute value, I'd make it a +2. Well, I have a -1 here, a y value of -1. I want to make it positive. So I'd plot it at +1. Right? I have a point here. I could kind of eyeball it, I guess. But at some point, you try to find a clean value somewhat. 0.5, -0.75. So 0.5, +0.75. Right? Then its counterpart as on the opposite side, -0.5, +0.75. What ends up happening is that little bit of graph between -1 and 1. So the part of the graph, y equals x squared minus 1, but only the part between -1 and 1. I'll make it a different color, and I'll make it dashed. Only that part is going to get reflected over the x-axis if I find the absolute value of this function. All right, the parts that are already above or on the x-axis are going to stay put. So going back to my original function, y equals x squared minus 1. If I were to graph that as y equals the absolute value of x squared minus 1, see my new graph, the blue one, I'll make it a little thicker. We'll go 5 on that, and I'm going to go with the dotted. That new graph is exactly what you would expect to have happen. The parts that were above the x-axis stay above the x-axis. The parts that weren't get reflected so that they are. All right, and they match up with the points that I supposed were probably true. All right, so that's how you graph an absolute value function. You could really do the same thing with trig functions. Not so much, well, you could do it with exponential functions, but you need part of it to be below the x-axis. So, but I'll show you a quick trig example. Sine of x. So it's a sine function, right? The parts that are below the x-axis, so y less than or equal to 0, that part, any part that's in the green here would have to get reflected up if I took the absolute value. So y equals the absolute value of sine of x. See, any part that was below got flipped to go upward now. Any part that was already above stayed above. Right. So that's a little taste of the relationships that exist for absolute value functions. Now, how does that apply for this problem? Well, it tells us that if I'm looking at a graph, even if I don't know its equation, and part of it is a part that's below the x-axis, all I would need to do is take that part that's below the x-axis and reflect it to be above the x-axis. So this piece here needs to come on up. I don't know if I can grab it. Well, maybe I can. I can't. It doesn't let me flip. All right, well, this piece here needs to get flipped over and put on the top end. Yeah, that's the one drawback in this app. Or maybe it's a drawback in my understanding of the apple. We'll see. But anyway, blue becomes red now. And what was a negative area of 1.5 is now a positive area of 1.5. So the net area is now 1.5, right? So what that's really telling me to do is to break up this integral into my two parts, right? 0 to 6, not 0 to 6, 0 to 2, and then 2 to 6. But the part from 2 to 6, well, that's equivalent whether it's absolute value or just the ordinary function itself, right? So this would be equivalent to this, all right? So then this is where things get a little more interesting. So we already know the 2 to 6 part of it. We figured that out before over here. That's equal to 5. This piece, an absolute value function can transcend the integral under certain circumstances, as long as it's consistently up below the axis over the interval or above the axis over the interval. It can transcend the integral, as in you can bring it outside of the integral, right? So we can do that in this case now because we've guaranteed that the entire graph is on one side of the x-axis, right? Whether it's entirely below or entirely above, we break it up by x-intercepts, right? So this could be thought of as the absolute value over the interval of 0 to 2 of f of x dx. And then close the absolute value. I'm going to make this look more absolute value E. And the benefit of that is that we already know what the antiderivative of 2 is, the integral over the interval of 0 to 2 is, and that is negative 1.5. The absolute value of that is a positive 1.5 plus the 5 results in a 6.5. But that's really only if you need to show all the notation, and most of the time you don't have to. But at this point, you know that I kind of go with the theoretical approach as much as I can, and then I show you the nifty shortcut way of doing things. Right. In this case, though, since you're dealing with an unknown function, you're kind of stuck with having to do at least some of the notation. Now, since we intuited that the net area was 1.5 up here, just by thinking about absolute values, we could have jumped straight from this computation or this notation here to this result all in one shot. I just wanted to show you, oops, sorry, arrow went to the wrong thing. I just wanted to show you what the notation would look like if you needed to itemize all your steps. And covering all the bases. All right, so the question is, why not go from 0 to 6 in one shot? Why do we have to split it into 2? Right, the integral over the interval of 0 to 6 is 3.5. If we just took the absolute value of that, we get 3.5. So one of the answers is it would just flat out give us the wrong answer. The other is the process of applying the absolute value function to an integral only works if the entire interval related to the integral integral, I know it gets a little much, but if the integral or the function over the interval is entirely below the axis or above the axis. All right. So going back to this graph, so let me just grab a snapshot of it real quick and bring it down. So over the interval of 0 to 2, just focusing on what we had there originally, the entire graph was below the x-axis. All right. It wasn't until we got to 2 that the entirety of the graph moved to be above the x-axis. All right. So that's our transition point for finding areas. Right. So it's at that point where I would say, all right, I'm going to find the absolute value of just this piece, but I'm going to leave this piece the way it is, because I could just find the antiderivative of the function. It's already absolute. It's already a positive value. So I can leave the antiderivative exactly the way it is initially over the interval of 2 to 6 of just the function f of x dx, and it's going to report the correct answer. It's this piece that I got to worry about. Right. So in order to do that, I need to differentiate between the two parts. Right. I could show you very quickly another one before we do E, just because I want to nail this point home. I'm just got to think about where I'm going to put it. I'm just going to, I'm going to steal some space over here. Let's say, for example, you have a function f of x. I'll give you a real function, something that we can verify. Let's say x cubed. I want something that's going to have multiple. Actually, I'll do a trig function because I already have one on the screen here. It should work. I was going to do a cubic, but I'll do a trig function. Let's say we're doing that. Really, this function would be fine. So f of x is equal to the sine of x over the interval of negative pi to pi. All right. And let's say I need to find the antiderivative over the interval of negative pi to pi of the sine of x, but as an absolute. All right. So of f of x, I'll actually even write it as f of x, because we know what f of x is. All right. So if I want to use the approach that I was just talking about, the first thing I'd have to know is where over this interval there's going to be a change in sign. Right. So we know that the sine function, SIGN sign. So we know that the sine function is negative. And that's just from graphical investigation, from negative pi to 0, but then positive from 0 to pi. Right. So what I would do is I would break up this integral to go from negative pi to 0 with the absolute value of the function still intact. But then the remainder of the interval from negative pi to pi, the remainder of that interval would be 0 to pi. I can just apply it to the ordinary function. Right. And then I would simplify this further by saying, well, once I figure out the antiderivative over the interval of negative pi to 0, I can then find the absolute value of that answer and then add it on later. Right. So we're looking at absolute value. And I'll show you what it would look like if you were to just find the antiderivative of f of x dx over the interval, just like kind of treating it like this function just with a negative pi here. You'll see that it'll give you a net value of 0, and that would be a problem. So the absolute value of this plus this whole other piece the way it is, right? All right. So then I would need to anti-differentiate my function. The antiderivative of the sine function is negative cosine. So negative cosine over the interval of negative pi to 0, but an absolute value there, plus negative cosine over the interval of 0 to pi. Dang it. All right. So notation wise, it gets a little crazy because I have an absolute value. This is absolute value notation, but then I have my given notation here, given that x is equal to 0, x is equal to negative pi. That can be a little annoying, but and it is what it is. The standard notation that's used. So then I would substitute in my values. I'm gonna clean this up. Maybe I'll do it a different color, make it pop. I'm just kind of butt this up against it so it makes it a little bit more obvious. And then these are my absolutes. A little cockeyed too. Make it a little longer. Okay, well, not gonna get any better. So plug in a 0. Negative cosine of 0. So negative 1 minus, plug in a pi, negative cosine of pi is negative 1. So negative 1. So a lot of parentheses here. Plus, and the other piece, negative cosine of pi so negative cosine of pi is going to be negative 1 minus negative cosine of 0, which is going to be a 1. So I have negative 1. Well, I got 3 negatives here. So minus 1 absolutified plus positive 1 plus 1. So I'm going to get a 2 plus 2, and that's going to give me a 4. All right. Whereas if I took the antiderivative over the interval of just negative pi to pi of the sine function, saying forget it, I don't need this absolute value stuff. I would have gotten 0 because this is the net area, right? I have equal parts below the axis and above the axis. However, if you reason through it, you would say, okay, well, if it's symmetrical and I know that the area under the curve between 0 and pi, right? So the area under the curve between 0 and pi, so I could say 0 less than or equal to y less than or equal to f of x. What did I not call it? I never called it f of x. No, look at that. There we go. That area, if I know that that one's going to be positive and it's symmetrical, then I would just double it. If I wanted to find the total area, once I realized that finding the absolute value of the sine function is going to give me equal parts area on the other side, that would be it. All right. Now, another thing to keep in mind is that Desmos is way better at math than we are because it's programmed to be. So since it can graph an absolute value function, odds are it can actually evaluate aspects of that absolute value function also. So if it was like a multiple choice question on an assessment, let's pop in the absolute value function. And it'll just spit out the answer, right? But this is a little taste of the theory behind it, right? Because again, this is telling us the negative becomes positive, and it's this area. When we're finding an absolute, it's this area that we're trying to find. All right. Theory being the word of the day. But the absolute value would leave, yes, exactly. Absolute value would leave the integral between 2 and 6 unaffected, exactly. Right, and in this case, between 0 and pi. Right, same general theory. Right. So teensy tiny notes, just because I want to be able to actually do the problem that was here also. The average value of f over the interval of 0 to 6. So average value of a function. If you remember, we talked about the mean value theorem for derivatives. There's also really a mean value theorem for antiderivatives also. But it's way simpler in terms of what you have to do. It's way more complicated in terms of what it all means. But I think I probably hit you with enough theory for one night. So let me just get into the strategy here. If anybody needs this example later, I'll come back to it. But if you want to find the average value, so average I don't know why I all capped that, but average value, the formula is 1 over b minus a times the integral over the interval of a to b of f of x dx. Right. So really all you're doing to find an average value is you're just dividing your net area by the length of the interval. Right. So in a contextual situation, I think I hope I did anyway. I usually use snowfall as my example for an accumulation of area. So like if 100 square miles had a coating of snow on it after 1 hour, and 200 square miles have a coating on it after 2 hours, and so on. Like you can see the accumulation of area. We're gaining more and more area as time goes on. Right. But if after the 2 hours are up, I wanted to know on average how much area is gaining snow per hour, I would take the amount of snow coverage at the end of the period of time. Let's say after the end of 2 hours, I have 200 square miles that are covered with snow. Divided by the 2 hours, we're looking at a rate of 100 square miles per hour. Right. So if I were to extend that on and say, all right, well, after 1 hour, I have 100 square miles. After 2 hours, another 100 square miles, but then it melted a little bit. So I lost 50 square miles. So now I'm down to 150 after 3 hours. Then I gained another 100. So I'm up to 250 after 4 hours. Then I gained nothing for the next hour, but I'm still keeping time. So I'm still at 250 square miles after 5 hours. I would just divide the 250 by the length of the interval of 5 and say that I'm gaining, or I have a net gain on average of 50 square miles per hour. Right? So that it's really just a matter of dividing it by the interval length. So that's what the 1 over b minus a is. So in this case, I have an a value here, a b value here. So 1 over 6 minus 0 over the interval of 0 to 6, f of x dx. We've already figured this out. Actually, we didn't even figure that out. They just told us that. That was 3.5. Yeah, that was right in the open, 3.5. So that 3.5 multiplied by 1/6. All right, so 3.5 divided by 6, 7/12. Okay. And that's all the question's asking, because again, we knew over the interval of 0 to 6, the net area, the net accumulation decumulation was 3.5. So that amounted to, if it's a length of 6 over the interval, 7/12 per unit of horizontal displacement. Right. So then on the next page, we get to some more trig problems. Now it gives us a relationship here, but you kind of look at it like, all right, these must just be for fun, because you could type this stuff into the calculator. I can even show you. I mean, as much as this diagram looks glorious here. Integral over the interval of pi to 2 pi sine x, close it up, dx, and you see, oh, I did pi to 2 pi for some reason. 0 to pi, what I meant to write. How did I get pi to 2 pi? I don't know. Well, in case you wanted to know, 0 to pi is 2. Right, so that was given to us, but we could have figured that out. Oh, I did pi to 2 pi because that's part A. That's where I was looking. All right, so in a periodic function, f of x dx, there's symmetry all over the place. Otherwise, it wouldn't be periodic, right? So what we're saying here is over the interval of 0 to 2, right? So over the interval of 0 to pi, we have an area of 2, right? So 0 less than or equal to y less than or equal to f of x. All right, those would be all the top side values or areas, but I only want going from 0 to pi. All right, so it's just this little piece here. All right, but that tells me what each arch is worth. Each arch is worth an area of 2. So if I know where the bounds are going to place me in terms of the graph, all I have to do is account for above the axis, below the axis, and I'm good to go. All right. And because there's symmetry there, even within the arch, let's say we have x equals pi over 2 is half the distance between 0 and pi. Good enough. The integral over the interval of even 0 to pi over 2, well, if the whole thing is 2, that's literally half of that area. So that area going from 0 to the dashed line would have to be 1. Right? So we know a whole lot about the sine function now based off of that information. Right? So all I'd have to do is determine where pi and 2 pi are. Since I already accidentally kind of figured that out, we already know. But in Desmos, it's really nice because if I change the step in the graph to be consistent with units of pi that I see in the problem that I'm dealing with here, and it looks like every unit of pi is either pi over 2 or pi itself, except for this weird one here. I'll get to that in a minute. But I could just make my step pi over 2. Whenever I'm in doubt, I usually make it pi over 12, because 12 is a common denominator for all the denominators in the unit circle. Right? So it's a good value to have as a scale. But now I'm in pretty good shape, because from pi to 2 pi, you see it's the same region as the one that's shaded here just below the axis. So -2. 0 to 2 pi, that's equal parts above the axis and below the axis. So that's an area of 0. From 0 to pi over 2, that's half of the arch, which has an area of 2. Half of 2 is equal to 1. Just by having a sense of what's going on with the graph, it makes things a whole lot easier. Now, in the cases of D and E, you look at it and say, oh, okay, now things are getting spicier. But remember, we can break up an integral by the addition. Right? This is some property. So I can write this as the integral over the interval of 0 to pi of 2 dx plus the integral over the interval of 0 to pi of sine x dx. This we already know is equal to 2. They told us that. And this is a constant. That's what I was talking about on the previous page. With a constant, all you have to do is find the difference between the bounds and multiply it by the integrand. So 2 times the difference between these two bounds. So 2 pi. 2 pi plus 2. Right? So these are nice little sight recognition situations that can kind of, well, it'll save you time, but it'll also save you some effort. Like in E, I have a constant multiple. I'd write that as 2 times the integral over the interval of 0 to pi of sine x dx. Again, they told us this was equal to 2. So 2 times the 2 that's out in front, and you get a 4. Now, in geometry, if you multiply one dimension of a two-dimensional figure, a regular figure, by a value, you multiply the area by that same value. So here I'm multiplying the height by 2, so I would multiply the area by 2. If I double the width, I double the area. If I double the height, I double the area. If I double them both, then I quadruple the area. Right? So the little geometry rules that get you a long way. Right? The next one's kind of weird, but it's actually pretty easy. It just doesn't look like it would be. So if I plot, I'll call it g of x, sine x minus 2, you see that all it really is a shifted value. Oh, I'm sorry, shifted graph of the original function. Right? So the bounds, you'll notice, are actually shifted also by factors of 2. So let me plot those for you real quick. If I plot, I'm just going to turn these off. I'll leave that on. No, actually, everything else is fine. But I'll plot x equals 2 and x equals pi plus 2. It's kind of tough to see, so I actually will shut everything else off. But the bounded region that I'm concerned with is actually the same as the bounded region in the first graph, this green region here. Okay? That green region just got shifted over along with the graph. So this is actually the same as the integral over the interval of 0 to pi of sine x dx. Okay, because this is a translation to the right 2 units. All right, and that happened here and here also. All right, so this is going to give us a result of just a 2. All right. Now in G, well, sine is an odd function. So let me get rid of some of this stuff here. Go back to the original sine graph. Which means, and I'll just focus on this part here, it means it's symmetric over the origin. But it also means that if you have equal distance to the left as to the right from the origin, you're going to accumulate the same amount of area, just negative versus positive. So those areas will always offset each other, no matter what the function is. Right? So I can even show you real quick. If I were to say, instead of the sine of x, I would say the sine of x squared. You can see, well, actually, that's not an odd function anymore. Bad example. I'm out. let's say sine of, I'll just keep it simpler, 3x. You have equal parts negative and positive as you go to the left versus as you go to the right. All right. So for this function of u, and so actually now that I think about it, I just found an example of where this wouldn't work. So we would have to stipulate where u is an even function of x. We'll take that as a typo. That's a legacy typo. That's been there forever. I've had this since the beginning. But bottom line is it's going to be a net area of 0. Right. Now, sine of x over 2, that's a frequency of 1/2. That means that it actually takes double the length to complete a sine wave. Right. But that's all fun fact of the day. Oh, that's fun. Fun fact of the day territory. Let me actually just show you. Y equals the sine of x over 2. If you compare the graphs, I'll just focus on this part. You'll see in the space that it takes to complete one full wave for the sine of x, we're only getting half of the wave for sine of x over 2. Right? So really it's like, okay, well, what does that mean? Well, it goes back to what I was saying before. If you double the height, you double the area. If you double the width, you double the area. If you double the height and the width, you quadruple the area. Here I'm doubling the width, right? So I would double the area. It's just a question of area of what, right? So over the interval of 0 to 2 pi, I'm getting really this arch just expanded to be double width, right? So this would be equivalent to twice the area over the interval of 0 to pi of sine x dx. All right, which is going to be 2 times 2, which is going to be 4. All right, that's a weird one, but it's also something you could verify using the integral function on the calculator. It's just visually, it kind of pops out at you. Right, this arch is now expanded to be double as wide, but the same height, same maximum height. So naturally, that would give us double the area. All right. So then I would be a cosine function, but a cosine function, well, we could do this one of two ways. I mean, all of these problems we could have just chucked into a calculator and called it a day. But if we want to kind of learn from the process, it sort of begs the question, okay, how can we do this in such a way that we'll get a meaningful understanding of the geometric applications of a derivative, antiderivative. So we can take a look at the cosine function and how it compares to the sine function. All right, so now it gets pretty messy here, but if you look closely, you might remember this. A cosine function is just a shifted version of a sine function. All right, if I take the sine function and shift it over by pi over 2 units, if I shift it by subtracting a pi over 2, it'll take my cosine function, my sine function, and shift it to the right. But if I subtract a pi over 2, add a pi over 2, it'll shift it over to the left, right? So the cosine function can be written as a sine function, right? So here's my cosine function. this is my shifted sine function, right? What this is telling me, if I want 0 to pi of the cosine of x, that's really the same thing as saying 0 to pi of sine x plus pi over 2 dx. Right? So we could write it as a function of sine. Right? That could be useful. But the thing is, I need cosine over the interval of 0 to pi. Right? So when I shift everything over, all I'm getting, at least in my shading here, I'm getting my function also shifted by pi over 2 units. All right. So if I shifted everything over, I'd have to account for that in my shading, but that's kind of neither here nor there. In fact, I even have this set up to only go down to the x-axis from the positive f of x. So you can just visually inspect, though, and see that over the interval of 0 to pi, you have equal parts above the axis and below the axis. All right. So either way, you'd come up with 0 as a result, whether you looked at the shifted sign or the cosine function itself. The reason why I figured do it as a shifted sign is because then you wouldn't have to worry about learning all the different things and relationships associated with a cosine, because they really are the same relationships. It's still the same area under the arch for a cosine function as it is for the corresponding sine function. It's just a horizontal shift, right? Numbers 4 and 5 are not going to worry about, so that's where we're going to actually kind of end it for the course. What I wanted to do is just go through the practice test. I'm just going to toss these. You wouldn't. There's not. These problems are not going to be on the test or final exam or anything, so I wouldn't worry about it. You'll get plenty of exposure to those kind of problems in Calc 2. Sorry, sip of coffee. All right, so I'm going to stop this recording.